Okay, in the last section of 3.3, we're going to be looking at Cramer's rule. Okay, and so this is kind of a tacked on section here. We have a lot of ways to solve linear equations at this point. We have a lot of different methods. We have row operations, we have our calculator, those are the big ones. Cramer's rule just gives us another tool in our toolbox, okay? So if I have a linear system, okay, or a vector equation, looks something like this, we should be familiar with at this point. Okay, so I've got my variables x1 through xn, I've got my vectors v1 through vn equal to some b, okay, and this corresponds to a system of equations, okay. System of equations would look something like this, right? I've got x1 times, let's call it a, x2 times b, and that would carry on for however many I have to where I have some b1, right? That would be good components of my vector b, and I would get n such equations, x1 times, let's call it c, x2 times d, out to b2. Now we'll continue for however many equations we have. Now, as we look at this set of equations, each vector contributes some piece to this solution. Okay, each v1 has its a piece of b, v2 is a piece of b. They all contribute and work together. Okay, so Cramer's rule uses our matrices. So our matrix A is going to be our coefficient matrix. Okay, and then we're going to have matrices that are A sub I, which are going to have the vector B replacing the ith column of A. Okay, so he said each one of these has its own component, so we're going to use that idea that we take this vector B and we help locate that sort of component to the solution. Okay, so let's look at a quick example here. So I've got 3x1, and I'll show you kind of what the pieces are here and what you use them for, because I still haven't found x yet. Okay, we're going to need these two matrices to find x. Okay, 3x1 minus 2x2 is equal to 4. And then negative 6x1 plus 4x2 is equal to 1. Okay, so this is my system. Okay, my coefficient matrix A, I can write pretty easily. It's 2 by 2. It's 3 minus 2 minus 6 and 4. Okay, and so now I need to write my vector B. Let's go ahead and write that down so I can help see how it fits in with my A sub i's. Okay, so I've got two unknowns here, x1 and x2. So I'm going to have two A sub i's. I'm going to have A sub 1. So in A sub 1, I'm going to take this column that's B and replace the first column. So I get 4, 1, negative 2, 4. And then I'm going to do the same thing in A2. I'm going to keep the first column from A. So 3, negative 6 gets kept. Negative 2, 4 gets replaced with the B column of 4, 1. Okay? All right. And then each x sub I that I'm looking for, x1, for example, is going to be the determinant of A1 divided by the determinant of A. Similarly, x2 then is going to be the determinant of A2 divided by the determinant of A. Okay, so you can see I need these determinants. Okay, so the determinant of A is going to be 3 times 4 is 12 minus negative 6 times negative 2 is a positive 12. So it's plus 12. I get 0. Okay, so that is a problem, right? That means I don't have a solution to this matrix, right? Because I can't divide by 0. Okay, so notice these two columns are actually multiples of each other. If I multiply this by 3/2, I get the second column. Okay, so notice Cramer's rule only works if A is invertible. Okay, so you can only use Cramer's rule if A is invertible. Okay, now we're still ultimately going to do this. We're just going to tweak our problem so that we no longer have a situation where I'm invertible. So I'm going to switch this to 14. Okay, instead of 4. Okay, I want to get you the idea. Got to be invertible in order to use Cramer's rule. Okay, so 14 then becomes that number. Okay, it gets replaced in A2, so it's not an A2 at all. Okay, so let's get a new determinant for A now with our new values. Okay, 3 times 14 is 42 minus 12. That's going to be 30. So there's the determinant of A. Okay, the determinant of A1, 4 times 14 is 56. 56 minus a negative 2, so that's 56 plus 2, that's 58. And then my determinant for A2 is going to be 3 times 1 is 3 minus a negative 24. So I get a positive, 27. Okay? So now I can write what x1 and x2 are. x1 then is going to be A1, which is 58 over 30. Okay, that's 29 over 15. And x2 is going to be 27 over 30. So that is 9 over 10. Okay, so you can imagine if I do the row operations on this matrix, that gets pretty sticky. Where here I can just do these multiplications. I only have to divide at the very end and get those simplified fractions. Okay, so that gets me x1 and x2 using Cramer's rule. Okay, so let's do one more with Cramer's rule. Then we're going to talk about some geometric relationships. Okay, so I've got negative 5x1 plus 3x2 is equal to 9. I said one more 2 by 2, and then we'll do one 3 by 3 as well. And then I have 3x1 minus x2 is equal to negative 5. Okay, so my matrix A is the coefficient matrix, negative 5, 3, 3, negative 1. A1, again, we're going to take this 9, negative 5 and replace the first column. So A1 is 9, negative 5, 3, negative 1. And A2, we keep the first column, so negative 5, 3, but then we replace the second column with 9, negative 5. Okay, now we need to find these determinants. So the determinant of A is going to be 5 minus 9, negative 4. The determinant of A1 is going to be minus 9 minus a negative 15. Okay, so that's minus 9 plus 15. That's a positive 6. And then the determinant of A2, we're going to have minus 25, or positive 25, sorry, negative 5 times negative 5 gets us positive. Minus 27, so that's a negative 2. So now I can find x1 and x2 using my Cramer's rule formulas. So x1 is going to be a1, which is 6, over the determinant, which is negative, over a, which is negative 4. So I get a negative 3 over 2. And x2 is going to have a2 on top, which is negative 2 divided by 4. So I get negative 1/2. So there's my solutions to the system, negative 3/2 and negative 1/2. Okay, so that is Cramer's rule for 2 by 2. Now let's go ahead and expand this thinking to a 3 by 3. Okay, we know how to take the determinant of a 3 by 3, but we certainly will know that it's going to take us a little bit longer. Okay, it's not going to be quite as quick. Okay, so if I have 2x1 plus x2 is equal to 7, negative 3x1 plus x3 is equal to negative 8, and then x2 plus 2x3 is equal to negative 3. Okay, so notice there are 3 variables there, x1, x2, and x3. So make sure you account for that when you write down your coefficient matrix A. So I've got 2, 1, 0 for the first row, because I have 0 copies of x3. Second row is going to be negative 3, 0, 1, because I have 0 copies of x2. And the bottom row is going to be 0, 1, 2. Okay, so there's A. My vector B, remember that's doing the replacing here, is 7, negative 8, negative 3. So now I can write down what A1, A2, and A3 are. So A1, taking 7, -8, -3, putting it in place of row 1. So 7, -8, -3. Then the rest of it's unchanged. 1, 0, 1, 0, 1, 2. A2, we're going to have 2, -3, 0. Replace second column. Keep the outer columns the same. A3 now, we're going to replace the far right column. So 2, -3, 0 is unchanged. 1, 0, 1 is unchanged. And then we put 7, -8, -3 in the far right-hand column. Okay, so there's A1, A2, and A3. Okay, now I'm going to need the determinants of all these. Okay, so don't rush yourself. Okay, feel free to use the calculator. Okay, when you do that, you should get that the determinant of A is 4. The determinant of A1 is 6. The determinant of A2 is 16. And the determinant of A3 is -14. Okay? So again, take your time finding those. Feel free to use a calculator. There's a determinant command in the TI calculator that you can use to your advantage. Okay, so x1 then is going to be 6 divided by 4. That's 3/2. X2 is going to be 16 divided by 4. That's 4. And x3 is going to be -14 divided by 4. That's a -7/2. So there are my solutions. Okay, you could write those as a triple: 3/2, 4, -7/2. Okay. All right, so I told you there's one more thing in this section, and that's volume. Well, before we get to volume, we need to talk a little bit about area. Okay, so let's start with a really easy parallelogram, let's call it, but it's actually a rectangle. It's even better than a parallelogram. So this first vector here is going to be A0. Okay, so it's a scaled version of the identity vector, right? The identity vector is 1, 0. The other identity vector is 0, 1. Okay, so we're going to put those together. And we're going to look for the area of this space. Well, I know this side length is A, and I know this side length is D. So the area of that rectangle should be A times D. But I also know if I have these two vectors, I could make a matrix, A times 0 and 0D. And if I take the determinant of this matrix, I get A times D. Okay, now if I switch these vectors around, so I do, 0D and A0, well, now that would seem to make the determinant AD, but the area should still be A times D. So you can take these two vectors that are part of your parallelogram, or your rectangle in this case, and simply set them up as a matrix, and you'll produce the area of that parallelogram, okay, with respect to absolute value, okay? So the area is equal to the absolute value of the determinant of A, where A is your vectors, okay? So let's look at an example here of a parallelogram. This first coordinate is at 3, 5, okay? And this second one here is going to be at 7, 1, okay? Now, naturally, they would add. We talked about a parallelogram rule when we talked about adding vectors. And if I add those pairs, I'm going to get 10, 6, right? 7 plus 3 is 10, and 5 plus 1 is 6. So 10, 6. Okay, that looks nice. So now if I want to find the area of this parallelogram, I simply need to take the determinant of the vectors, 7, 1, and 3, 5. Okay, and you can do them in either order because the area is going to be the absolute value of that determinant. Okay, so 7 times 5 is going to be 35. Minus 3 times 1 is 3. I get 32. I'll go ahead and write an absolute value there, but then it's positive. So the area of this parallelogram is 32 using determinants, using linear algebra. Okay, so you just have to set up your, now the only catch is this center point, this back point has to be at the origin. Okay, you've got to get one of those points to the origin. So you may have to shift your rectangle around You know, if you add it, shift it up and down and up to the right or down to the left or both, okay, it's still going to have the same area. Okay, that area here was 32. Now we can expand this to volumes. So in a volume, you know, imagine I have 3 vectors here that form the corner of a box. Okay, so this is the very corner. This is the near corner of a box, right? This box continues out, okay, in such a fashion. Okay, so I have this very corner of a box. I put one corner here at the origin. Okay, then I take my 3 vectors. Okay, so for this example, my 3 vectors are going to be 4, 0, negative 5. Okay, I could write them vertically. I'll go ahead and write the next one horizontally just to show you we can use either notation. 1, 4, 4, and then my third vector will be 6, 2, 0. Okay, so I have those 3 vectors. I'm looking for the volume. So the volume, again, is going to be the absolute value of the determinant of these vectors. So 4, 0, negative 5, 1, 4, 4, 6, 2, 0. And I just need the absolute value of that determinant, okay? So I'll show you a little bit of the calculator here. Okay, so we're going to use a calculator here. So we're going to use a calculator here. Type in this matrix. I've got 4, 1, 6, 0, 4, 2, and then negative 5, 4, 0. Okay. And I'm going to go to matrix, go over here to math, and the very first one there is DET for determinant. Take the matrix A, do that determinant, and I get 78. So my volume of my, it calls it a parallel pipoid. Okay. So it is a parallelogram or a rectangular prism, you might call it. It just means a 3-dimensional square solid or square-edged solid, okay? So you just take the determinant of those matrices. Now, think about if I have dependent vectors. So if I get a determinant of 0, what that means is this corner of the box isn't actually a corner. It's just a plane because only 2 independent vectors just gives us a plane. So if you think about a plane has no volume because it has no thickness. So when you're flat, you're going to get that volume, okay? When you're flat, you're going to get that 0 volume, which tells you that one of your vectors is dependent, okay? You do not have dependent vectors. Now, the other idea we want to notice here is that if I have a parallelogram, okay, so I create my parallelogram here, and I cut this parallelogram in half. Now I have a triangle. And this triangle is exactly half of the original parallelogram. So what you can do then is you can just take the determinant and divide it by 2 to get the area of the triangle. So if I go back to this one we did with 3, 5, and 7, 1, this upper part, once I do the determinant, I get 32. Half of it then would be 16, would be the area of the triangle. So you can use halves to find the area of triangles as well within the same concept of using the determinants to find areas and volumes, okay? All right, so I told you chapter 3 was a fairly short chapter. 3.3 in particular is a pretty short section. It's things we've talked about. It's kind of an add-on material, okay? Get you thinking about Cramer's rule is, again, that programming background is easier to program because computers can compute determinants relatively quickly. It's just multiplication. And so with that programming background, Cramer's rule makes for a fast way to solve for a solution, okay? Depending on your computing power and your skill and things like that, okay? So that's the end of chapter 3. We'll start with chapter 4 next time, where we start talking about vector spaces, and I'll see you then.